Okay, welcome back to B110 Continuum Mechanics. Last time we talked about material continuum and the concept of a continuum and the governing field equations that we will be deriving in continuum mechanics that are used to solve for the equilibrium and mechanics of continuous solids and fluids. The underlying foundations to these continuum laws are Newton's laws of mechanics, and we know that Newton's laws are not universal, but they certainly apply precisely and exactly under all the engineering and bioengineering conditions that we will be interested in. So today what we'll do is we'll do a bit of a review of Newton's laws. We'll do it fairly quickly, and then that'll give us some chance to do some problems afterwards. So let's start by considering a material particle, call it P, with mass m in Euclidean space. And the position of that particle in space is going to be identified by its coordinates in a Cartesian reference frame, so an origin here. And the vector x is the position vector of P. So its coordinates represent the position in this Cartesian frame of reference of our material particle P. We'll assume for now that the mass of the particle is constant, and we refer to this as an inertial reference frame. And so in this inertial reference frame, we can define other properties and vectors. So v, the velocity vector, will of course be equal to the derivative with respect to time of x. Then the derivative with respect to time of v will be the acceleration vector. In order to develop Newton's laws, we also need to consider the force acting on the particle, the total net force acting on the particle, and so we will label that vector F. So particle mass m, with position vector x in an inertial reference frame, has external force F acting on it. Given this, we're in a position to write Newton's laws. So let's start with Newton's first law. Remember, this is the one that says that a body in motion remains in motion. So that translates in our notation to if F is equal to 0, so there's no external forces acting on P, then V is equal to a constant. Newton's second law, this is the famous F equals ma, is the case when F is not equal to 0. So when F is not equal to 0, then the rate of change of linear momentum of the particle, so ddt of linear momentum, which would be mass times velocity, is equal to F. Now, because mass is constant, that means that F is equal to m dv dt, which of course is ma. And so this is the famous F equals ma, or I like to write it as the force balance, F minus ma equals 0. The external forces and the inertial forces balance. So ma is called the inertial force. That brings us to Newton's third law. For this we need to to consider, instead of one particle, a system of particles. So let's consider a system of k particles that we'll label with the index I. 1, 2, up to k. And now we'll let Fij be the force of interaction exerted by particle j on particle I. And therefore, Fji must equal the force exerted by I on j. And these, of course, are both vectors. So Newton's third law amounts to, for every action, there's an equal and opposite reaction. For every Fij, there's an equal and opposite Fji. So Newton's third law can be written concisely as Fij equals negative Fji, or Fij plus Fji is equal to 0. Before we go on, let's label F equals ma as equation 1, and Newton's third law is equation 2. Now let's consider the case when I equals j. Then of course Fii must be equal to the negative of itself, which means that it can only be 0. Using that, let's consider the total force acting on particle I. So that's not just due to one other particle, but to all of the others. So that would be F sub I would be equal to an external force, for example gravity, plus the sum of all the interaction forces, which would therefore, we could label the external force as F superscript E sub I to indicate that it's acting on particle I, plus the sum from j equals 1 to k of Fij. Where when j equals I, the contribution of Fii will be 0. But now, let's use Newton's second law to equate Fi to the rate of change of linear momentum of particle I. In other words, we now have d dt of mi times vi equals Fe sub I plus the sum over all the interaction forces from the particles j equals 1 through k, and this holds for all particles I equals 1 through k, and we'll call this equation 3. Therefore, the motion of the system of particles is described by a system of ordinary differential equations, one equation per particle. To go further, we would need to specify how Fij is found. In other words, we would need some sort of constitutive law specific to the system that represented the forces of interactions between the particles. For example, if the particles were interconnected by springs, then the spring constant of each spring would allow us to determine what the force was as each particle moved. Or there might be another sort of field, like a magnetic field, that would determine the interaction forces. And so it is with continuum mechanics. When we generalize from a discrete system of particles to a continuum with an infinite number of particles, we'll obtain partial differential equations instead of ordinary differential equations, but we will also need constitutive laws to describe the material properties that represent the interactions between the particles within the material continuum. So we have the universal laws of mechanics, and then we have the constitutive laws that are specific to the particular material that we're analyzing. So a special case of motion is the case when there are no accelerations for any of the particles in the system, and such a body is said to be in static equilibrium. At equilibrium, with no accelerations, equation 3 is going to simplify. And becomes f sub I external plus the sum from j equals 1 to k of all the interaction forces is 0 for all the particles I equals 1 through k. Now if we sum this over all the particles, now we get the sum of all of the external forces plus the sum of all the interaction forces for all the particles is equal to 0. Now if we think about this, sum over all I and all j, for every fij there's an equal and opposite fji, and for every fii is 0, which means this sum is 0. So this leaves us with that the sum of all the external forces acting on the system must be 0 for a body in static equilibrium. So in summary, we can say that for a system in static equilibrium, all the external forces acting on the system sum to 0. So we'll pick up from here in class to review moment equilibrium, and then we'll do some examples. We'll see you then.